Well, thank you for the introduction, and it's really a pleasure to be here today. Thank you, everybody, for joining me. And I'm very excited to be here in January, so I hope that as you watch this talk, you're keeping in mind ways that we might be able to collaborate or sparking new ideas. So today I'm going to be talking about the design of robust robotic hands for ocean exploration, and in particular, these hands for this humanoid robot. Over 70% of the Earth's surface is covered in oceans, but NOAA estimates that we've only really explored about 5%, which means that as we're really missing out on a vast library of biotechnology, of bioinspiration that could lead to new technologies like medicine. It also means that as we reach deeper and deeper for more food and energy resources, it's hard to fully understand the impact this has and ways that we can take to mitigate damage. And finally, it leaves a lot of lost history, from early human coastal settlements to deep sea shipwrecks. But there's a good reason why we've only really explored about 5%. It's really hard. Here's an example of a suit that can take a person down to about 300 meters. And just for reference, the deepest part of the ocean is beyond 10,000 meters. And so this really means that robots have the opportunity to revolutionize the way that we interact with our oceans and what we can understand about them. This is the humanoid platform that has inspired my work. It was really directed by Osama Khatib in the AI lab at Stanford University. And the idea behind this project is you're creating an intuitive humanoid platform that even a novice user can operate. And they can feel the forces that the robot is feeling through this haptic interface. And so you can sit down and have a very intuitive feel for how the environment and the robot are interacting. And this is footage from the maiden mission to the La Lune shipwreck off the coast of Toulon, France, at a depth of 91 meters. These are actually cannons here. And this was a really exciting mission for us because we were able to validate the platform. We were able to acquire a vase, an artifact, and bring it back up to the ship. But this video, it masks some of the realities that robots face when brought into real unstructured environments. It doesn't show when there were really strong water currents pushing on the body of the robot, pushing it into the ground or into those cannons I pointed out. And so what you really need is a robot that's not only capable of all the tasks that it needs to perform, but it needs to do it in an extremely robust and reliable way. Because if, let's say, the hands fail at depth, you compromise the feasibility of this platform. So there are two very important requirements. So what are the tasks that this robot needs to perform? The initial motivation for Ocean One was looking at coral reef through long in situ experiments in the Red Sea. So here are some divers doing this sort of process. And they take the coral reef samples and they put it in the structure and then come back over time to do service on the setup. So what does that mean for us? Well, we're going to have to be able to handle, let's say, these small samples. We also need to be able to handle the structure itself, as well as possibly tools in order to service it. And then finally, it might be really helpful if you're doing a really precise task with one hand to ground the robot with the other. And so you're going to have to be able to control the body of the robot given one hand, which could have quite large forces. And then some special conditions you're likely to see, hello, welcome. You're likely to see a large range of friction coefficients. So you can often see very slippery, slimy biofilms that are covering objects that have been in the ocean for a long time. But you could also see really abrasive rock materials. You also have buoyancy. So you could, and this is a bit unique to ocean environments, you could have a very massive object that's also floating that you could push away. So this is something that we consider later. You also need to think about the fluid dynamics of manipulation. And many groups have started thinking about what's the fluid dynamics of arm motions in the water, but we really look at what's happening in the hand. And then finally, you have large changes in ambient pressure. And this is what makes it dangerous for humans to dive to great depths, but the robot also needs to be able to withstand this. So because of the need and the importance of bringing robots into marine environments, there are many projects that have sought to do this. And a lot of work has to go into making this a reality. You need to have good mission planning. You need to be able to have multiple tethered robots working together. You also need to think about navigation and communication, which is very difficult in deep sea environments. And then once you get to where you want to go, how do you even do station keeping? That in itself is a challenging problem. And so while some groups have thought about specific hand designs, it's not quite as many. And this is a growing field, and so I expect to see more hands coming out soon. But they tend to be somewhat specialized to very particular tasks. So this is one of my favorite examples. It's the Harvard Soft Gripper, and they're showing it actually manipulating a really squishy organic creature in the ocean, and that's super cool. But now imagine that this hand needs to hold a large structure. It might not be as strong or precise at doing that task. So still today, when a more generalized hand is needed, these robots typically default to single degree of freedom grippers because they're extremely robust and reliable and can do a lot of tasks pretty well. But for us, when we're looking at, let's say, an archaeological site, it might be kind of scary to have this gripper reaching towards your priceless, delicate artifact. So that might not be the best solution for us. So before going into the design of the hands for Ocean One, I'm going to give a little bit more background and context for how we talk about and design hands. And in particular, underactuated hands are highly sensitive to the compliance in the system and contact conditions. So I'm going to go into first, how do we select, both passive and actively select our compliance in the Ocean One hand? But also then, how can we look at contact conditions? And once again, can we actively change our contact conditions given that we're underwater in interesting ways? And then finally, a couple concluding remarks. The human hand is a really amazing tool, and that's why for decades people have admired it and tried to mimic it. And this is a patent from 1919 of an underactuated design. And even today, really the vast majority of hands have multiple fingers. So there are these fundamental things that we hold on to. And the field of dexterous manipulation, in my mind, really breaks down into these three primary areas: hardware and kinematics, dynamics and control of the hand once the body is set, and then grasp planning and higher level strategy. And all of these must work in concert to create new exciting robotic strategies and technologies. But I live primarily in hardware design and kinematics. And so that's why I find it fascinating that the human hand exhibits underactuation, which is this idea that you have fewer actuators than you do degrees of freedom. Degrees of actuation than degrees of freedom. And so you can actually see this with your own hand. So if I were to command my fingertip to curl, it'll do something like this, where these two joints will curl in unison. But then if I add an environmental constraint, say my other hand, now just the tip curls. So that's two very distinct behaviors with a single input command to curl. So there are a couple really practical reasons why you would want to include this in your design. You can make your hand more lightweight if you have fewer actuators. Actuators can be quite heavy. You can make your design more robust if you have fewer moving parts. Let's say you have fewer tendons. Tendons can be pretty easy to break, so you might want to reduce the number. And then you can also simplify your control. Intuitively, if you have fewer actuators, you have fewer inputs to control. So that's really all I'm saying. So because of all these reasons, there are a lot of underactuated hand designs proposed. And here are 5 that are well known in the field of underactuated hand design. But they typically fall somewhere on the spectrum, where at one end you have a high degree of underactuation. You're likely to see these very soft materials, and they're going to adapt really well to weird shapes. On the other end of the spectrum, you will have a lower degree of underactuation, and you're unlikely to see those same soft materials, but you're going to get a lot more precision and firmness when grasping. So this end is excellent for handling structures and tools with strength. But it might not be the best option if you want to, let's say, hold a piece of fruit where you really don't want to bruise it, and it could have a really organic shape. And then, of course, there are designs in the middle that try to trade off and rather draw from capabilities on both ends of the spectrum. And so, for example, this hand has soft joints and rigid phalanges. So how does this compare to what we see in the marine environment? You once again see this sort of specialization, where at one end you have very soft continuum-style fingers that are hydraulically driven, and on the other you have stiff bellows and a linkage-driven design. So this is where the Ocean One hand comes in. We want to have a hand that can be tested in the field, that is robust enough for ocean environments and doesn't sacrifice capabilities from one end or the other. So how do we go about, what's the design challenge here? There's a vast literature out there on grasping and dexterous manipulation theory. And the key idea is that you control how hard you squeeze the object or your internal grasp forces. And this then lets you control how much friction you're getting at the contacts. And then this can allow you to do whatever function you need to, which could be resisting forces that would push the object out, or it could be moving the object in your hand. And this is a relatively straightforward idea when you have a fully actuated hand, when you can plan for and execute specific finger motions. But this is not strictly true with underactuated hands, where now the way that your hand closes around an object depends upon the interaction with the object, and that's what we saw with our own fingers. And so now, because of this interaction, when you're designing a hand, you need to carefully take into account the specific tasks that this hand is going to perform. And this inherently makes underactuated hands quite specialized to specific sets of tasks. And so I'm going to look into two properties of underactuated hands for this talk. Because underactuated grasping is highly dependent upon the compliance in the system and contact conditions. So compliance could be structural if your finger is made of aluminum versus silicone rubber, but it could also be distributed, for example, how you choose stiffnesses for different joints. So to show the importance of this, here are two identical hands. The top one has its softest joint at the tip, and this one has the softest joint at the base. And as they close, they have not only different closing speeds, but final poses. And that's one parameter changed. Now, contact conditions, most people think of this like friction, but I would also argue that it also has to do with where contact is likely to occur on the hand. So it might have to do with the shape of the phalange. Now, to show the importance of this one's more intuitive. This is a very slippery object, and this is an object that's more frictional. And the slippery object gets pushed out of the hand, and the more frictional object goes into a stable grasp. Okay, so now that we're confident that these parameters are really important to the function of an underactuated hand, let's start thinking about these as an opportunity. Because although we have to select them in the design process, if we're able to add even simple mechanisms that alter them just a little bit during operation, we can now have hands that can address different classes of objects and tasks. So the sensitivity limits us, but it also gives us an opportunity in design. So before moving on, I just want to state that for highly underactuated hands, you're typically losing the ability to do very fine in-hand manipulation, like flipping the pen in your hand. And you're instead going to be using the manipulation capabilities of the arms to do the more complex task. And the hands are going to be relied on more to grasp it or pull the object into a stable equilibrium, and then hold on to the object, or to resist external forces or inertial forces. So what are some of the methods that people take around hand design? Well, it makes sense to look at the human hand because it's so versatile. And some people try to classify, well, what are the different strategies that people have learned to take? You could also say, well, what are the ways that we simplify our control of our hands to be able to do many different cool types of grasping? But this is inherently limited to a somewhat humanoid form. You can try to reach out from that, but you're going to be somewhat limited. And so when you now want to break free from that completely, you have to actually go about testing your hand, grasping many different objects. And so it makes sense that people would try to standardize this by creating sets of objects that different labs can share to try and compare how different designs work. But as you can see, this is a household set of objects, and this just highlights that experimentally it's infeasible to test every object in the world. And even as we think about ocean exploration, we might not even know exactly what all the objects are going to be before we interact with them. And so that's why dynamic simulation is such a powerful tool for underactuated hand design. And because of this, many tools have been developed and have kept up with this trend of designing underactuated hands. My personal preference is to use SimGrasp. It was actually developed in parallel with the Ocean One hands. by a lab mate of mine, Shishuan Wang. And so if you're interested, please look it up. It is just very flexible and easy to use, and it's easy to parametrically change object, controller, and hand design parameters through many batches. So it's just, it's my personal preference. And so the point of this, though, is now you can not only test many different objects, but you can also test many different hand designs. So here you're seeing the addition of fingers radially in the hand and trying to compare that to how much force it takes to pull it out vertically. And so that really you can test many different scenarios quickly. But of course, there are limitations to simulation as well. Friction is really important for underactuated grasping, and it's difficult to model. So it's important that you ground your simulations in reality by comparing it to experimental results, and that's the approach that we take here. So now that we know that underactuated hands are very sensitive to compliance and contact conditions, let's go into how we actually select and actively change compliance in the Ocean One hands. So this is the design of the Ocean One hand. It has a single actuator, and this shaft runs along here and attaches to these 3 tendons. Now, all 3 of the fingers have 3 rubber flexure joints and 3D printed plastic phalanges. And the key functionality that we identified as sort of a minimum set is power wrap grasping, because structures and tools will often have these long extruded features. And then also pinching, because there are going to be objects that are too large or too small for us to wrap our hands around successfully. And if we were able to do these 2 things very well, then we give the operator a library of options to choose from. So let's start thinking about what the different compliant elements are and how they relate at a very high level to the functionality of this hand. So that's why we're going to start with a very simplified model. And so if we think about pinching, these are the fingers here, and if they're straight and the hard stops are engaged, we assume that this is a rigid beam. At the fingertip, there's going to be, let's say, a skin, and so that will give a compliance, a stiffness at contact. You also have a stiffness at this base joint, and that's going to relate some input torque to some motion of the finger. And then if you have 2 fingers and only a single actuator, you might want to have a system that shares loads between the 2 fingers. And a pulley is actually a physical way that some hands implement this. And you could have a spring here that biases it to the center, such that if your fingers go off to the side, they'll want to come back to the center. And just for the sake of simplicity, let's set the dimensions to 1. They would act as scaling factors if they were not. So external grasp stiffness is one way to start thinking about the precision of a hand. And it's the scaling factor between a force applied to the object and the displacement of the object in the hand. So if you have a very large external grasp stiffness, you can apply large forces to the object and get very small displacements. So that would be a very precise hand. And all I want you to get from this equation is that it's a function of all of the stiffness elements in the hand. So now let's relate this to some hands we actually see designed. This is the Harvard SDM hand. And this is the case where our differential stiffness goes to 0. So it has a pulley system, a pulley differential, but it does not have a biasing spring. Now in this case, our external grasp stiffness acts as if our contact stiffness, our skin, and the joint stiffness were springs in series. And in this hand, I'm assuming that the joint stiffness is much softer. So your precision is going to be dominated by your joint stiffness. Now, let's think about what happens if our joints get very stiff. It takes a lot of effort to close the hand, right? And so that means that there's a trade-off between precision and motor effort. Now, in the case of the Ocean One hand, and this should make more sense later, we have the case where our differential stiffness goes to infinity. So we're actually creating a positional constraint. And in this case, we get an external grasp stiffness that is now independent of joint stiffness. And you'll see that we take advantage of this. We can get away with having really, really soft joints so that our motor effort is low without sacrificing our precision. So let's go into the kinematics of this hand. There are the 3 fingers here, and each one has its own tendon that has a spring in series with it, and that's what couples it to the input motion here. And so, and each finger has 3 joints. This base joint is broken up into 2 because we're including the lateral compliance, and the base joint is going to have the largest effect on fingertip motion. So the way that we go about designing this hand is first with the fingers, because that really determines what's the behavior, what's the curling behavior of the fingers. And we want it to curl first at the base and then the next joint. And that's because we want to be able to pinch inside small crevices. So given that, how do we actually do it? Well, we want our joint to be really soft, right? Because we want motor effort to be low. But we also don't want a saggy finger. So we need to have some preload at the joint that we need to overcome, and that's right here, in order to start the motion of the joint. But then we want the second joint, the middle joint, to curl after the first one, so we need a bigger preload. But again, we can get away with having a really low joint stiffness. And the same with the distal joint. And this is what gives you sequential curling. So let's compare this to the actual implementation. You can see that the proximal joint and the middle joint actually do pretty well. The distal joint, we had to make some concessions because there's a very small packaging size. And just for reference, this line here is the lateral stiffness of that base joint. So how do we actually accomplish this? We use a preloaded spring. So we take the spring and we stretch it before fastening it. So that's what creates the preload. But then as the joint curls, the moment arm of the spring decreases. So you get a really interesting nonlinear behavior, which is most prevalent or prominent in the middle joint. And that approximates what we hope to get. And in fact, with this, we are able to do straight finger pinching of very small objects, as well as wrap grasping around many different object sizes and shapes. And this actually, many of these objects come from that Yale CMU Berkeley set that I showed on a previous slide. Okay, so now let's assume we have set the design of the fingers. We know what their compliant behavior is going to be. How do we go about now designing the compliance of, how do we select the stiffness of this transmission? Just to give you a sense of the range of possibilities, if this spring becomes rigid, what's going to happen is that all of the tendon lengths must be the same. On the other end of the spectrum, if this spring becomes very, very soft, infinitely soft, it's the case where all 3 tendon tensions must be the same. So that's a really wide variety of options. You know, how do you choose something in the middle? Do you choose something in the middle? And so I like to think about this spring in series with the tendon as sort of making an elastic tendon. I find that very intuitive. And so if you, let's say, wanted to have this grip, where this finger is at a very different pose from this finger, this one has to have a shorter tendon. So that means this one must be stretched more. So I don't know if that makes it more intuitive, but that's how I think about it. So now then, how do we start thinking about this stiffness while including the more complex kinematics and compliance of those nonlinear finger joints? Well, one way to start thinking about this is with a force field. And this is the static force balance at each of these points. So if you take a point here, the object is fixed. You curl the fingers around it, you add up all the contact forces, and that gives you the force vector here. And so when you have a very light region, that means that your contact forces are low. And when you have a very dark region, your contact forces are high. Now there are 2 different plots here. This bottom one is the stiffer case, and it's normalized to the compliance of the tendon, which is quite stiff, but you're not ever going to get it completely rigid. And then therefore, the 4% stiffness, normalized stiffness, is much softer. So now then, let's look at point A with the soft transmission. The fingers are able to curl, and in fact, they have different tendon lengths, and they were able to wrap around the object. And in fact, all the contact forces are low, and the sum of the contact forces is also very low. And so I would say that with real friction, as a hand is grasping things, an object is likely to stay at this location. It's probably not going to get pulled farther into the hand. And there's a large region. So I would assume that this is not a very precise hand. And that's in comparison to point B, which is actually the same location, but with the stiff transmission. And in this case, the fingers cannot curl over and touch the object. So only one finger is in contact, and you get a very large force trying to pull this object in. And so I would say that this is probably a very precise grasping hand, because the region in which objects settle is much smaller. So that's looking at a static force balance and trying to relate it to dynamic grasping. So let's think about this a little bit more. I like to think of acquisition region as a floating rope in the ocean. Now, if you're a robot trying to grab onto this thing and there's water currents, your body's going to be pushed around, and it's going to be really hard to stay still. But even if you get really good at that, the rope itself might be floating in unpredictable ways. And so the chance that you get your hand perfectly around the object before grasping is pretty low. You're going to be off by a little bit at least. But even if you are able to get it in the right location, you're going to want to grasp really fast because you don't want to mess around and take a really long time and then have it float away. So that's speed and being far away from the hand. So let's think about grasp region experimentally. So to simulate this floating rope, here's a PVC tube and it's hanging from the ceiling, so you're actually looking up at the ceiling. And its starting location is designated by the dot, and a line shows where it finishes. Now, if it's purple, or magenta, then that means that it's touching the palm. And that's in comparison to a pinch grasp, where once again, the dot designates where it starts, but it does not touch the palm in its final location. This is the overall grasp region for the soft transmission and the stiff transmission. And you can see that in the soft transmission case, where all the blue dots are pinches, first, there's a lot of pinching going on, and where they settle is over a large region of the grasp region. And that's in comparison to the stiff transmission, where you don't get very much pinching, and when it does pinch, it's in a much tighter area. So this is what we would expect to see. But not only that, we can now do this in sim grasp, where we're able to see once more that there's a lot more pinching with the soft transmission, and it's more likely to settle in different locations as compared to the stiff case. So this is just to show sort of the power of this option in analyzing new hand designs. Okay, so that's our ability to grasp, to pull objects in. What now about our ability to hold on to objects or maintain a grasp? Let's stick with the same PVC tube, because like I said before, this sort of extruded feature is going to be quite common on structures and tools. And if we pull this object out horizontally, you can measure the force it takes to displace the object a certain distance. And so this gives you a force trajectory curve. And in this case, the pink line, which is the stiff case, and in fact, the line is the mean of 5 trials, and the shaded region is the standard deviation. The stiff case outperforms an intermediate stiffness and the softest 4% stiffness case. And this makes sense because you're back driving this single finger here. And once again, you can emulate the same results using sim grasp. So far, all I've told you is that you want a stiffer transmission, right? You can acquire objects more precisely, and you can hold on to these structures and tools better. Well, let's look at a couple counterexamples. I really like this cone. So what we're doing is pulling up on the tip, and it's rotating out kind of like this around a pivot point at this side of the palm. And so what we find is that the softer transmission in blue outperforms the stiffer transmissions, especially at small rotational angles. And what's happening, you can think about it like this. So if I were to have this object, and I'm using my precision fingers to hold on to it, it's going to be really easy to torque this object. But now if I substitute my middle finger for my pinky, it's really easy to resist moments. And that's because my pinky finger is far away from the pivot point. So I'd like you to walk away from this talk feeling like your pinky finger is really strong. And so this finger here is acting like our pinky. And it's far away from the pivot point, but it's also on the object where the diameter is smaller. So it needs to have a shorter tendon length. And that's what makes it such that the softer transmission engages that pinky finger better. Another case is this goblet, which has a stem right here. And so intuitively, you would want this finger, this pinky, to nestle into that feature such that when we pull the object out horizontally, it performs better. And once again, you see the softer transmission outperforming the stiffer transmissions. Now, there's one last case that I include because I just think it's really interesting and unintuitive. Here's a block. It doesn't have any interesting surface features to nestle our fingers into. But as we pull it out horizontally, the stiff transmission in pink outperforms the softer transmissions. And it's because you have these edges on the object. And even very small changes in contact conditions or forces at those contacts can make a really big difference. And in fact, as these fingers get pulled to the side, because we have passive compliance, you get a slight increase in the contact force, which significantly improves your pull-out force. And so all that I really want you to take away from this slide is that you want both. And in fact, you often see that either the softest option or the stiffest option gives you the most strength. So how do you choose one or the other? You know, and you don't really want this intermediate option because it's kind of always mediocre. Well, you don't have to choose. We do this using a Dual-Stiffness Winch system. So this is the input shaft here, and there are the 3 tendons sticking off like this, and this is a single winch unit. Now, if we open this up, you can see that there's a shaft collar that rigidly attaches it to the shaft. Torque needs to be transmitted through this spring to the pulley, so you have a spring in series with your pulley. But this is only one spring, so how are we getting both behaviors? Well, it uses this idea of spring contraction, where the spring actually will change its diameter as it flexes. So in the spring preferred direction, which is being shown here, it's what I call what the spring was manufactured to do. You get a decrease in the radius as it flexes, and it's free to do that because there's space. So it'll start really soft, but then it'll hit an inner race, and it won't be able to decrease its diameter anymore, and it'll transition from soft to stiff for behavior. Now in the opposite direction, in the anti-preferred direction, and you were to take these and try to wrench them open, the diameter is going to increase. And so in this case, you have a wall around the outside, and it's not able to do so. So you go straight into the stiff behavior. So now you get very, very different behaviors, basically fixing tendon length or fixing tendon tension based solely on the direction that you wind your tendons. So this gives you 2 very different possibilities. And we found this to be really important in the field. During tests, we found that as we were coming into objects, there was often a lot of uncertainty. And if that's the case, and there's strong water currents around you, there's a good chance that you're gonna hit your hand on things because it's extended from your body and you're reaching out for the world, right? So basically the worst case scenario for a tendon is if your hand comes in and smacks like that, because you get the shock going straight through it and it's gonna snap, unless you have passive compliance. So when approaching this object, I would very much suggest that the operator use the soft transmission mode. But now if you want to lift this object and it's very heavy, it's full of samples and boulders or rocks, you now want to transition into that softer mode, or to the stiffer mode. This was also an interesting case study where the operator's reaching for this object and they're so focused, it's awesome, and they're able to actually pick it up. And for this object, I would suggest, it could be heavy, there could be sand in it. I would use the stiff transmission to give you more strength. But now look at this hand. The operator is not worried about the hand at all, but it's essential that they ground themselves to do this precise task. To protect these fingers, once again, I would suggest that you go into the soft mode so that those tendons can stretch and move around a little bit. And that's all well and good. That's a very, I've had a lot of experience with this hand, so I think I could give suggestions to the user, but that's not a very formal way to talk about how to control this hand. And so that's where dynamic simulation with something like SimGrasp really shines, because now you can start testing all these different scenarios. So let's go back to the tube, and before we were pulling it out horizontally, now let's look at it in many different pull-out angles. And that would be alpha down here, where before we were at 90 degrees, and over many different transmission stiffnesses. And you see in this case that there's an optimal work to pull out, so that's integrating the force over distance curve, at about 60 degrees. So this will tell the controls engineer, the person designing the higher level primitives of the robot, that maybe you don't want to pull vertically up, and maybe you don't want to pull horizontally, but at some intermediate angle, and that's going to give you the best performance. Okay, so we know that underactuated hands are very sensitive to the compliance in the system, and we've talked in depth about this, but we're also really sensitive to contact conditions. So let's move on to that and specifically talk about how we can maybe improve our contact conditions given that we're underwater? So the idea here is that you can add something like suction flow to the fingertips of your hand. And just to give you a reference point, this is about the flow rate that we're talking about. Very, very gentle. So it's not like we're just taking a vacuum cleaner and sucking everything up that we can get the tube on. But really, this is such a light force, maybe 1 Newton of suction force, that you're still going to be relying on the fingers and the arms to do the strength of this manipulation task, whatever it is. And you can add, pumps are heavy, so you could add them to the shoulder of the robot so that you're not adding unnecessary inertia to the end effector. So this is a feasible option. But I do want to specify that this is not a suction cup, which is a common misconception. And there are a lot of really cool suction cup technologies being developed. But the main difference is that you can influence the object with the flow before contact occurs. And it can influence even very porous objects where you can't create a seal. So the idea is that you're inducing a flow around the object or between the object and the surface, and this creates a light attractive force. And just because we've talked a lot about compliance, you can in fact, maybe let's say choose a very stretchy silicone tube and fasten them in a way that they can double as the spring elements on your fingers. So you don't need to have these big loops of tubing getting caught on the environment. So this is the artifact that we acquired from the Laloon shipwreck, and it's covered in a thick, slimy biofilm. I was actually really surprised when I got to handle it. I was worried I would drop it and everybody would be really mad at me, but I didn't. And so something that's analogous to this in our daily lives is a bar of soap. So we tried it. And with this particular hand, with these fingers, we were not able to pick up this bar of soap just by squeezing harder. But we were able to do it very easily by adding suction flow to the fingers. And I think that this is a very, very intuitive idea, so I'm not really going to go into why and how it's working. But I do want to note also that we found that your coefficient of friction actually increases with suction flow. So it's a twofold. You're not only getting normal force, but you're also getting this coefficient of friction increase for certain objects. What I find more interesting is this idea of dynamic acquisition with suction flow. So here's another, what I think is an intuitive case. It's a light Lego piece, and it happens to get pulled into the fingertip at a location that's very convenient for pinching. Isn't that nice? And so now you can start thinking about contact conditions not only in terms of friction coefficient, but where contact occurs. And this is a bio-inspired idea. Suction feeding is ubiquitous in ocean environments, and you pull in water, and with it comes prey. So now what we'd like to ask is, okay, Lego pieces, yeah, okay, that's great. You don't need to fish around for it. But what about larger objects and more massive objects? That's less intuitive. When is suction helpful and when is it not helpful? How do we guide future designers? And really what we're asking is, what's the role of water drag and object inertia? So let's go back to our floating rope case, acquisition region. And now we're going to test it experimentally in a tank of water because we want to include water drag. So we have the exact same PVC tube, and now it's neutrally buoyant with a little bit of foam. And there's a very light magnet that will break free even with a little bit of rocking in the water. And we grab the object with multiple starting locations. The large dots are 3 successes out of 3 trials, and the smallest dots are 1 success out of 3 trials. And just for reference, this is the approximate size of the hand relative to this grasp region. So if we want to try to model this, and we do it without drag, we underestimate some of these regions. In particular, these regions out here, where the object needs to move a large distance and quite quickly in order to be acquired. But when we include even just a simple model for water drag just on the object, we're able to capture these outer regions much better. So not only can we do it, but it improves your acquisition region, which is a nice side point. Now, if we want to start looking at how suction flow changes this, we need to have an understanding for what's going on at the fingertip. So this is the suction force that we're measuring using a load cell. So this is the load cell data here over a distance. So that's taking a flat plate and the fingertip and changing the distance between them. And I just want to point out that this scale is very small. This is 1 millimeter. So these are really small scales, especially as compared to a hand size. And this point up here, so our experimental setup has just a little bit of flexibility. And so at these small distances, it starts to vibrate, so we exclude that data. But we do take a single point with a free-floating finger on the surface and pull it off with a force scale. So we want to include two parameters when we're trying to model this. The first one is the fact that you have flow going between two flat plates. And because the scale is small, we assume that the geometry approximates two flat plates. You get a pressure drop across this interface, and when you integrate it, you can estimate the suction force. But flow will change as the pump gets restricted. So this is using experimental values for flow. And you can see that as Q goes to 0, this parameter also goes to 0. So we need to include another one. And in this region, although your flow is really small, the distances are also so small that the velocity of your fluid is quite large. So viscous effects are going to start to matter. And so we assume that the pressure that the orifice is experiencing is being applied directly across the orifice area to the surface. And when you add these together, you actually get pretty close for a relatively simple model. And although this region is really complex with viscous effects, we assume that a line is close enough for the purposes of robotic hand design. Okay, so now that we have an understanding of what's going on, we can now look at suction flow in our simulation. And we find that there's this thin region on the outer areas that's increased by having this very light 1.2 Newton maximum force of suction flow. And it comes to about 27% here. So what does this now mean as we look at the mass of the object? Oh, let me first show you. So it's not really intuitive exactly what this means. It's hard to physically visualize it. So I'm going to show you a single experiment from this location. And without suction, it is a very decisive failure. But with suction, you have a chance. It's really far away from the hand, and you still have a chance to actually acquire this floating rope. Okay, so now we've looked at a very light, small object and a more massive, slightly larger object. Let's stick with this geometry and now investigate how mass changes the influence of suction flow. So this was the grasp region that I showed before of the 27% increase. And you can see that suction flow helps you up to at least 1 kilogram of mass, which is pretty significant. And in fact, you get the most benefit near this transition point. So what that tells me is that, okay, yeah, maybe if you're trying to ground the robot, so the robot's about 200 kilograms, suction flow is not going to do a lot of help. But if you're in this intermediate to lower region, it might be worth considering. It's not just Lego pieces. But now what we want to say is, well, okay, what if we do want suction to help in this region? How much do we have to increase suction flow? Is it unreasonable? So let's increase flow by 50%, and let's increase the maximum force that it can apply by 2 times. In this case, we do see an increase in the grasp region, especially at this transition region. So that tells me if I want to handle if I want to handle heavy objects, I'm going to have to consider adding a lot of suction flow. But even what's more interesting is this region here, where you don't see much benefit from adding more suction flow. And there's an argument to be had that you want to try and minimize how much suction you're using because you're going to bring up more dirt, you're going to suck it into your lines. You might want to reduce how much suction you're applying. So in fact, I would argue that there isn't much benefit to adding more suction flow. And this can hopefully guide future designers. So one last point that I'll leave you with before we finish is that this is actually possible to use this as a tactile sensor. So one very straightforward idea that I kind of alluded to is you could be sucking up dirt or things that you don't want to. And in fact, vacuum cleaners often will measure the flow that's going through them in order to know when they've been clogged. So this makes a lot of sense. And what's so cool about this is that you can add your sensor, let's say at your shoulder, right before your pump. So you don't need to be adding electronics or wires anywhere on your arm or hand. But it's a little bit more than that because you know where your orifice is located. So this tells you about where contact is happening. And this is a really cool thing because In underwater environments, you're likely for it to be murky, for it to be dark. There could be overhangs or things obscuring your vision. But even so, if I were to hold this object here, you don't know if my thumb is in, I mean, you guys know that my thumb is in contact, but a robot might not know. And so even just binary contact sensing in the clearest of environments can be really useful, especially in teleoperation. And tactile sensing underwater is really hard, especially in the deep sea, when you're changing depths, because that changes ambient pressure. And a lot of force sensors, tactile force sensors, are actually pressure sensors, and they'll saturate. So you need to start thinking creatively about tactile sensing in the deep sea. But it's even cooler than this, because you can now monitor the flow going through your tube over time as you manipulate or grasp the object. So here is a fingertip coming into a flat surface, and the blue line here is the angle that the fingertip is making with the surface. And this red line it's a differential pressure transducer that's estimating the flow. So as I come into the surface, you get a very clear contact signal. And as it comes up, you get these interesting dynamic stick-slip signals. And then you start losing resolution around this angle, around 20 degrees. And then as you come down and break contact, you get another very clear signal. So this is an area where I'm currently working with a younger student to further this. But this is just to show that there's a lot of potential around this and thinking about sensing technologies in non-conventional ways. So a couple concluding remarks. Okay, so underactuated hands are highly dependent upon the compliance in the system and contact conditions. And while this inherently tends to specialize underactuated hands to specific sets of tasks, it also gives us a great opportunity because we can start playing with how to alter these things in simple ways to then address different sets of tasks. And so for us, it was really how do we handle structures and tools as well as these sorts of artifacts that could have different sorts of shapes and properties. So we looked at how something like a dual-stiffness winch could maybe change how you share loads between your fingers, and how you might be able to use suction flow to change contact conditions underwater. And this is just the main takeaway, to really think about contact conditions and compliance as an opportunity to improve the adaptability of underactuated hands to these very versatile environments, especially in the ocean. And as we think about the hand and how it relates to the vision, the really big vision of bringing these robotic systems into the ocean, so much work goes into getting these robots where they need to go. The navigation, the control, the crews, the money and time. It's so important that you create manipulators, hands, that are capable and reliable to really make this vision a feasible reality. And then finally today, I've talked primarily about the design of the hands. How do we create the bodies in a very intelligent way such that they happen to be very good at what you want them to do? But I think this very naturally lends itself to also start thinking about tactile sensing. How do you know the state of the hand? And how can you think about tactile sensing as a design parameter when you're thinking about how to embody the hand? And then finally, this also lends itself when you start thinking about having a human in the loop to how to collaborate with that person to have this hand do what it's best at doing. So you might think about very low-level reflexes, given what we know about the capabilities of this hand, but that also allowing the user to make the higher-level decisions. So these are certainly areas that I expect this project to grow into. And then finally, I do want to make a plug for mechanical design in the robotics community. I think that it's a very important sort of marriage between making robot bodies that are capable and reliable to then allow controls engineers to take risks, to let the robots make mistakes and really do very dynamic, exciting things. So with that, there are too many people to thank. But of course, I need to thank my advisor, Dr. Mark Kokoski, who's just been an absolute pleasure to work with, creates an awesome environment. Dr. Osama Khatib, who is the director of the Ocean One project, and was just a great honor to be included in that team. And Dr. Allison Akamura, who has guided my research over the years and has been a great mentor. My lab mates, again, wonderful environment. I really love working with them. And in particular, Dr. Shishuan Wang, who I worked with in parallel with some of the parts of this project, and Dr. Daniel Akas, who got me started during my first year And then finally, all the very talented scientists and engineers that worked on Ocean One itself, building this platform up from scratch. And just, yeah, absolute pleasure. Funding sources that made Ocean One possible, as well as my own, I got blessed with a lot of fellowships during my time at Stanford, and that gave me the freedom to really stretch myself and try new things and take risks. So with that, I would like to answer your questions.